All right, let's jump right in. Today we're going to explore the absolutely wild world of nanotechnology to answer a question that honestly sounds like it's straight out of science fiction. How in the world do you control the flow of electricity one single electron at a time?
The key to all of this, the real star of the show, is a tiny bit of tech called a quantum dot. And scientists have this really cool nickname for them: artificial atoms. That's because, a lot like a real atom, they have these really specific, predictable energy levels. And that makes them the perfect building block for getting a handle on the quantum world.
So, okay, what is a quantum dot, really? Well, it's a semiconductor particle, but it is unbelievably small. We're talking just a few nanometers wide. And when you get down to that scale, the normal rules kind of go out the window, and quantum mechanics takes over. This gives these little dots totally unique electronic properties, completely different from their bigger versions. A great way to think of it is like a tiny man-made island just for electrons.
And here's where it gets really amazing. These weird quantum properties, they actually create something we can see with our own eyes. Get this, the color of light a quantum dot gives off depends only on its size. So your really tiny dots, 2 to 3 nanometers, they'll glow blue or green. Make them a little bigger, say 5 or 6 nanometers, and boom, you get orange or red. It's literally like tuning the color of light just by changing the particle's size. How cool is that?
Okay, so we've got our artificial atom, this little island for electrons. Great. But that brings up the next obvious and pretty huge challenge, right? How do you actually get electrons onto the island in a super controlled way? Well, to solve that, we have to talk about a fundamental concept that works just like an electron toll booth.
And that's really the heart of the problem here. You got to remember, we're not trying to manage a flood of electrons like the current in a normal wire. No. We want to be the bouncer at a super exclusive club, letting them in one at a time. I mean, how on earth do you even begin to get that kind of precision?
Well, the answer has a name. It's a phenomenon called the Coulomb blockade. And think of it this way. Imagine our quantum dot is a tiny one-person elevator. The first electron can hop on, no problem. But once it's inside, its negative charge basically puts up a force field, repelling any other electron that tries to squeeze in. So for a second electron to get on board, it's got to have some extra energy to push its way past that repulsion. It has to pay an energy toll. So that's the simple picture. The more scientific way to say it is that the Coulomb blockade is that electrostatic energy cost. Because the island is so incredibly small, adding just one single electron makes a huge difference to its overall charge. And that new charge creates a barrier, a blockade, right? That literally stops any more electrons from flowing, unless of course they've got enough juice to pay that toll and force their way on. All right, so if the Coulomb blockade is the rule of the game, the next question is, how do we build a device that can actually use that rule? Well, scientists came up with a really clever device to do just that, to basically harness this phenomenon. And it's a huge deal, paving the way for things like quantum computers. It's called the single electron transistor, or just SET for short.
An SET is built from 3 key parts. First, you've got the quantum dot. That's our island. Then you have 2 tunnel junctions. Think of these as the barriers, like the entrance and exit to the island. They're not solid walls, though. They're so thin that quantum mechanics lets an electron do something wild. It can tunnel right through. And finally, the most important part, the gate electrode. This is our controller. This is the toll booth operator who decides exactly when an electron gets to pass.
Okay, this is where the magic really happens. We've got all the pieces of our machine. So how does it all come together to work like an electron turnstile? Well, it is all about controlling that gate.
So let's start with the gate completely off. 0 voltage. Right now, the Coulomb blockade is in full effect. That energy toll we talked about, it's way too high for any electron to pay by itself. The barriers are up, the turnstile is locked down tight. Nothing's moving, no current. But watch this. Now we apply a tiny, very specific voltage to that gate. What happens? That voltage gives one electron, just one, exactly enough of an energy boost to pay the toll and overcome the blockade. So it tunnels through the first barrier, lands on the island for a moment, and then zips off through the second one. Click, the turnstile just moved forward by 1.
And this is the really elegant part. If you want to let a second electron through, you can't just keep the voltage the same. Why? Because now the blockade is even stronger. So you have to raise the gate voltage by another very precise amount to pay the new, higher toll. And that's the genius of it. It guarantees that electrons can only go through one by one every time you tick the voltage up a notch. Now, as you can probably guess, getting this kind of fine-tuned control is, well, it's not easy. For this whole electron turnstile idea to work in the real world, you have to follow some very, very strict rules. It's a tough game to play.
Basically, it comes down to two critical conditions. First, those tunnel barriers, their resistance has to be super high. We're talking over 25,000 ohms. That's to make sure an electron actually gets trapped on the island for a moment and doesn't just, leak out. Second, the temperature. It has to be crazy cold. If things are too warm, the electrons have too much random heat energy, and they'll have enough juice to jump the barrier whenever they want, completely ignoring our toll booth. So that energy toll has to be way bigger than any background heat energy for the whole thing to work.
And that really brings us full circle. What we have here with a single electron transistor is this incredible, almost unbelievable level of control over the most fundamental charge carrier in the universe. It's a tool that just blows the doors open for new kinds of computing and super-sensitive sensors. So I'll just leave you with this thought. When we can finally control the very building blocks of our electronic world, one by one, what are we going to build next?